And now we continue with a talk by Ben Gammage on introduction of 3D mirror symmetry. Ben?
Great. Thanks for inviting me to give a talk. I titled this talk Introduction to 3D Mirror Symmetry because I'm trying to spread the good news about 3D mirror symmetry. So I want, Denise is saying there's no sound. Can people on Zoom not hear me? Or no, can you hear me? Okay. Okay, so I want to spread the good news about 3D mirror symmetry. That that we have this sort of categorification of 2D mirror symmetry, and we have these two categories to play with, and it's all very exciting. And of course, the objects that I'm talking about are going to be things that the sort of objects I'm talking about are things that are going to be discussed in, I think, many other talks throughout this conference. So I'm going to try and sort of set the stage maybe for some of that material later on. So I want this to be a very friendly talk. I'd like people to interrupt me as much as possible. I want to make sure that everyone is on board and following along as much as possible with what I'm saying. And I don't want to go too fast, but I would hope to get to some sort of concrete examples at the end of my talk. So we'll see if that happens. But I'll do some examples in the middle of the talk as well. But first, let me sort of start off by setting the stage. And also feel free to let me know if I'm not writing or do not have these boards. I'll do my best, but I know it might be hard to see, so I'll try and write. So I'd like to set the stage by starting with I've written on the board the statement of what I would like to call 2D homological mirror symmetry, which, as is familiar to pretty much everyone in this room, I think, is the equivalence of categories between Italian category X and the category of coherent sheaves on some dual space X chip. So I've written a little story here. So what is this statement that I've written on the board here? This is an equivalence of categories of boundary conditions in topological twists. Maybe in the aim of writing big, I'll continue writing across this board, in topological twists of 2D n equals 2, 2 theories. Right, so the sort of physical origin of this is like in case when X and X chip are, say, mirror column manifold, each of those defines a nonlinear two-dimensional signal model. And those signal models have enough supersymmetry to do these topological twists, where sort of you get a pair of topological field theories called the 2D A model and the 2D B model. And we know from our sort of basic first course in topological field theory that a two-dimensional topological field theory, the data of such a thing is encapsulated in this category of boundary conditions. So to say that these topological field theories are equivalent is to say that their categories of boundary conditions are the same. Right, and those boundary conditions are on one side, they're going to be submanifolds in X, and on the other side, holomorphic submanifolds in X check, with vector bundles, blah, blah, blah. So, okay, so this is the sort of standard story of homological mirror symmetry that, just to give maybe a bit of history, right, the story of mirror symmetry begins sort of with enumerated mirror symmetry, where people are comparing some sort of numbers, and eventually we learn that like those numbers are sort of downstream of sort of equivalence of categories, possibly with some mechanisms. Like maybe you really want this to be an equivalence of Calabi-Yau categories or something. Ultimately, you want some equivalence of categories, and then you want to figure out afterward sort of various ways of producing other invariants from those categories. Okay. So why am I telling this story? Oh yeah, let me say that where do these 2, 2 theories come from? This sort of 2, 2 theory stuff comes from the fact that that X and X check are Taylor manifolds. Okay. Or now we have more general things like maybe X and X check are Hilburn models, whatever. Roughly speaking, it's something like this. Okay. So what's the story that I'm going to tell you today? I'm going to tell you what 3D mirror symmetry is. And so I told that prehistory a second ago, because I think that 3D mirror symmetry also has a prehistory, where people have been for a while comparing various invariants, categories, numbers, points of different systems. And the point I want to make is that a lot of those invariants are sort of just like the enumerative invariants of 2D units and we're downstream of this equivalence of categories. The enumerative equivalences of 3D unit symmetry are downstream of an equivalence of a pair of two categories. So I'm going to call these two categories X. This stands for CUDA, because we're going to study some CUDA maps. So I'll explain what that is a little bit later. And I'll call the B side 2 category KRS of X check. Maybe let me give these sort of fancy X's to indicate they're not the same Taylor manifolds anymore. Fancy X, whatever. So this KRS stands for Kapustin, Rosansky, Skolina, who wrote this paper along with a sequel by Kapustin and Rosansky, explaining what the two category of boundary conditions in Rosansky-Witten theory is. So I should say that some people call this two category also RW, for it's the two category of boundary conditions in Rosansky-Witten theory. Okay, so formally, the structure of this thing looks a lot like the structure of this thing up here. So what's the difference? There is now an equivalence of these two things are not categories, or rather they're two categories. But they're two categories of boundary conditions in topological twists of a pair of theories. Now not two-dimensional theories, but three-dimensional theories and 3D n equals 4 theories. So where do 3D n equals 4 theories come from? Roughly speaking, what you should imagine is that X and X check are now not Taylor manifolds, but they're hyper-Taylor manifolds. Or something else that we are going to need to consider is we're going to need to allow them to be, so hyper-Taylor to me is pretty close to holomorphic symplectic, right? These are complex manifolds equipped with a holomorphic symplectic form. So holomorphic symplectic. But not just holomorphic symplectic, but I'm going to need to allow symmetry groups. So in algebraic geometry, the way we do this is by saying I allow X and X check to be holomorphic symplectic stacks. Alternatively, I could say that X and X check are holomorphic symplectic varieties with a Hamiltonian G action. Right, so the stack would be sort of the G quotient here. So the basic fundamental examples that you should keep in your head are, and the sort of ones that have really motivated most of the theory, really are cotangent bundles. The examples here are supposed to be that X is maybe the cotangent bundle to an algebraic variety, or maybe it's the cotangent bundle to the quotient of an algebraic variety by some reductive group G acting on. So G you can think of as a complex D group, and B is you can think of as a complex manifold. Maybe in most cases that we consider, B is just in fact a complex vector space. So it's just a G representation. And so you can think of this thing, of course, as a I think I'm going to in this talk, I'm going to require X to be symplectic. So this includes so some Coulomb branches have full symplectic resolutions. I am not at this moment prepared to speak about what happens in the cases that don't. I think that's an interesting question, but certainly our knowledge of some of this material is even in simplification. So in more complicated cases, I'm not going to disagree. Yeah, so you can think of this T star B mod G as being, of course, like T star B. If B is a G representation, this has a Hamiltonian G action. So you can think of this pair of XG, or you can think of this cotangent bundle here in that sense. Okay, so these are the basic claims. So roughly speaking, you can think that, okay, 2D mirror symmetry was about an equivalence of categories between dual Taylor manifolds. 3D mirror symmetry is about an equivalence of two categories associated to dual hyper-Taylor manifolds.
So in 2D,
Yeah, okay. So the question is over here, like these could have been like Ginsburg models or something. What about in this case? What's the fullest generality I can say this in? I'll say that there is going to be. So later, let me postpone that question until later. I will say on the A side, there's going to be a sort of partially wrapped version of this category, which categorifies as sort of biacidal type categories, which appear from the Ginsburg. So that phenomenon at least will translate. Any other questions before I start explaining what these two categories are? Okay. So I better say some words about what these two categories are. So unfortunately, these two categories are not fully constructed in most places. The composition of Nancy and composition of Nancy Selena paper did construct a large part of this A side 2 category. This A side 2 category is still very much conjectural, although there's some nice work of John Metzger on it. But let me give you some properties of these two categories. So one is going to be that once again, well, let me put it this way. So the objects of these two categories, objects of this food X and KRS X are the most basic objects are going to be Lagrangians in X. Right, holomorphic Lagrangian submanifolds inside of X. Maybe I should just make that explicit. Holomorphic Lagrangians. Right, because this is a holomorphic symplectic manifold. And so, in what sense? So, okay, here I have two categories. Here I have two categories, and so the statement is going to be that that this food X and KRS of X both categorify, or maybe I should say they each categorify the holomorphic Lagrangian parts. Holomorphic Lagrangian parts of, respectively, the Fukaya category of X and coherent sheaves on X. So, right, if X is a holomorphic symplectic manifold, in particular, you can take the real part of its holomorphic symplectic form, you get a real symplectic manifold. Was there a question? No. You can take the real part of its holomorphic symplectic form, you get a real symplectic manifold that has a Fukaya category, but you can ask for Lagrangians, which are actually holomorphic submanifolds of X in its original complex structure, and also Lagrangian. So those are going to be some subcategory of the Fukaya category they generate. And similarly, if you look at coherent sheaves on X, you can ask for coherent sheaves whose support is actually a holomorphic Lagrangian. So yes, so I'm sketching out the sort of big pictures, but there are going to be singular. You can produce singular Lagrangians sometimes, or objects with singular Lagrangian support inside these categories. I'm just sticking to the sort of the simplest part of this.
Is there going to be precise?
In a case of interest to us, I will give a precise definition later on. And I'll in a moment give you a sort of slightly imprecise definition. Right now, I'm just sort of saying some properties. Let me state one more property, and then I'll give you a more precise definition. Not a totally precise definition, heuristic for what KRS is. But first, let me just say that one other thing we expect is that when I talk about decategorifications, one way to sort of decategorify a two category is there's a way of sort of a categorical taking a sort of HP in sort of periodic cyclic homology over yourself one categorical direction. And one thing that we expect is that if I take HP of this Spooner category, and if I take HP of the KRS category of the same manifold X, then these are actually equivalent. There's a sort of related statement you can find in Eric's notes on DT invariance. And this equivalence is expected, of course, to be the Von-Stevich-Sorbelin generalized Riemann-Hilbert correspondence. sort of in the sense that kind of, if I take the Hawkshire homology of this 2 category, it should give me the part of coherent sheaves on X that's supported in holomorphic Lagrangians. And then if I take periodic cyclic homology, it should deform that to the sort of TQ module supported in holomorphic Lagrangians. So again, these are some sort of rough expectations we have for those 2 categories. And sort of this is the way they might relate to some other material that people have been thinking about. So I just wanted to put that out there. And now let me sort of give some more precise statements. But in order to give a more precise statement, I first have to modify these. So more precisely, we actually are not just interested in these holomorphic symplectic manifolds X. When we define our 2 category, we're really interested in a pair. We consider pairs of a holomorphic symplectic manifold or a scalar manifold or whatever, together with a Lagrangian inside of it. Lagrangian. Sorry, I wrote that small. What's the meaning of this Lagrangian L? So on the A side, that is when I'm trying to consider what this Hilburn 2 category is, which I haven't said what it is so far. But on the A side, this L plays the role of a sort of non-compact skeleton. For those of you who are familiar with the sort of skeleton language of the categories, or a sort of stop for the record. So when I write down a pair X comma L and I ask for its Hilburn 2 category, I'm asking for a sort of partially wrapped 2 category, just like you can ask for a partially wrapped Hilburn category, where you stop it by the geometry of infinity. So it's possible that there's some sort of analog of a kind of Landau-Ginzburg type data that gives you this L, just as there is in the 1 category. We don't quite know what it is yet, but that's the role that this L is going to play on the A side. And on the B side, if I specify this L, what I'd like to do with it is I'd like to consider the 2 categories. So I'll call this KRX X comma L. And I would like to think of this as the 2 category generated. Let me assume that L is a union of smooth components. Then I can ask for the 2 category generated by smooth components of F. And so if L is a union of these smooth components, Li, union of smooth components intersecting cleanly, sorry?
Everything should have right.
Yes, everything is understood in the drawings. If this Lagrangian is a union of smooth components intersecting clean, then the Hom between any 2 of these Li, so Hom from Li to Lj, is going to equal the category of coherent sheaves on Li intersect Lj. So you can treat this as a sort of part of a definition of what this KRS2 category is, that if you're studying the sort of part of this KRS2 category that's generated by a bunch of smooth components whose intersections are all also smooth, then the Hom of Li to Lj is just coherent sheaves on Li intersect. And the Hom from Li to itself is just coherent sheaves on Li. And then you get this sort of compositional structure by some combination of tensor products on these things, some pullbacks and push points. Yes, so the one thing that I should say is that, yes, so first of all, this is imprecise because I really needed to say pullbacks, push forwards and twisted pullbacks when you define the composition. So I haven't written down the composition, but one thing that's in the KRS proposal is they propose to twist these categories. Alternatively, what you can do is you can sort of keep the categories the same and twist the sort of compositional structure by inserting appropriate tensors by the canonical sheet. So that has to do with sort of your choice of polarization. I think it's a bit technical to go into, so I'm not going to go into it now, but we'll give a complete definition of one of these KRS categories later on. And then, you know, everyone can, as homework, compare it to whatever model they well, we do, because I said that this was a smooth components intersecting clean. So if two components intersect cleanly, then the sheaf of vanishing cycles is just the constant sheaf. So if I take HP of this, then if I take HP of this thing, then I get Durand homology of the intersection. More generally, you would, if they intersected in the critical locus of F, then you get hybrid matrix factorization with appropriate cases. So I'm just trying to restrict myself in this talk. Everyone's asking me all these very complicated. I'm trying to restrict myself to the very simplest possible case. We can familiarize ourselves with what happens in the simple step. Okay. So I should, I guess, say something about this Buder-2 category. I think I can erase this board. Everyone remembers the statement at this point. It looks very similar to the usual mirror symmetry statement. So just to say something about the Buder-2 category. So the Buder-2 category. So I said that it's a categorification of the category of X. So it has the same object, sort of, insofar as Lagrangians, I mean holomorphic Lagrangians, but whatever. It has the same objects and one morphisms as the Italian category of X. Well, good question. I guess I just arbitrarily picked. This part is going to be very vague because we don't have a complete definition of Buder X. I mean, the answer is that you actually have to consider the whole S1's worth of real C but I don't want to get into that. I'm just sort of giving a rough picture of why this category applies to the category. Roughly speaking, you have objects or Lagrangians. You want to consider their intersection points should give you morphisms between them. And it's going to have some new two morphisms. Well, let me just say that the new ingredients telling you how to compose two morphisms. So I haven't told you about the two morphisms, but the way you compose them is going to be a count of three balls satisfying the Buder equation. So I'm going to count maps from a three-dimensional disk U into my symplectic manifold X, satisfying the Buder equation. Which is the equation. It's the most natural equation you could write down if someone gave you a three-manifold mapping to a hyperhuman manifold. Namely, it's I del X plus J del Y plus K del Z is equal to 0. So this is just to suggest that like this is all of the sort of new complexity of this category comes in the two morphisms. And so the construction of this category is still conjecture. So construction of this Buder-2 category of X is still conjectural. And the point of this talk, one thing you're supposed to take away from this talk, is that we are proposing a sheaf theoretic model for understanding. Yes. You propose a sheaf theoretic model. Okay, so I'm going to say this out loud because I don't want to get into the details here. But if I have two holomorphic Lagrangians, then I know there's this result of Verbitsky-Solomon that actually in a generic complex structure they don't bound any holomorphic in a generic whatever. So you might say, well, like then how is this sort of Kaya thing going to be interesting? And the answer is that in special complex structures like rotating a one parameter family, I will see it. And those new holomorphic disks I see that only occur, in isolated points in the one parameter family are the two morphisms in this Buder-2 category. So the three balls are going to have boundary condition on those special holomorphic disks. So I'm going to have holomorphic Lagrangians, and then they're meeting at points, and then there's these special holomorphic disks between them, and the ball is going to have boundary.
And is it clear that it happens at isolated points and not at the dense set points?
That's a good question. I think that I can't speak to it. I will say we have work in progress. I've been talking with Simon Rezchikov about this sort of case of T star C and T star C star. And we understand maybe some things about those, but still not very much. We're hoping to sort of give a complete construction of the two categories in this case.
You say that's you spherical start of something else.
Okay, first of all, yes, but second of all, eventually I'm going to use micro-locations. So,
Essentially,
well, so it's going to be inside, but well, I know we now have a definition of micro-local sheaves in a general Weinstein manifold. You can imagine that I do something similar here. Of course, really, I'm going to restrict myself to within bundle set. So, yes, exactly. So I need to tell you what a micro-local show. So that will happen at the end of the talk. Also, judging by my time so far, so okay, before I get there, let's give an actual example. So now I feel really bad. This is supposed to be like an introduction, and we're like, oh, it's a this is my program, and I worry that I've lost everyone. So let me kind of give an example of what's going on. This is everyone's favorite example. Well, it's my favorite example. Which is the case when X L, this pair, is the cotangent bundle of C star, and I take my skeleton L to be just the base C star of this cotangent bundle. So in this case, this Bruder 2 category, root XL, is, if you're thinking of it as you think of oh yeah, and there's another ingredient which I didn't mention, which is the rapid. Just like in the Fukai. So if you think of this as analogous to the setting of the Fukai category of the cotangent bundle, it should be reasonable to you that this Bruder 2 category is generated by a cotangent bundle. Little l, which I mean not bold L, which is the cotangent fiber to C star at some point, say the identity. So in order to describe this 2 category then, I just need to tell you what the endomorphisms of this thing. And the endomorphisms of this, as you wrap this around, is going to turn out to be just Z. Where what I'm thinking of is that this, I'm thinking of this as a monoidal category. So yeah, sorry, some chains on, I mean, some linearization of this monoidal category. So what I mean is that a basis for the intersection points, so the endomorphisms of L should be given by intersection points of L with itself, or really with a wrapping of itself. And I'm claiming to you that A, there are Z many of those. B, that they compose by just taking the sort of the nth one and the nth one composed to the n plus nth one, and there's no other difficulties with the composition. And furthermore, that there are no 2 modes. I mean, there's no further, there's no further things that you have to worry about. So this is a discrete category. Okay, so this is a sort of a very concrete thing. In other words, what I'm trying to tell you here is that this Bruder 2 category, XL, is equal to the 2 category of local systems of categories on C star, on the base of this cotangent bundle. Which again is what we know, what we're familiar with in Fukai categories. The Fukai category of a cotangent bundle is equivalent to the category of local systems on the base. Here we're saying this Bruder 2 category of a cotangent bundle is equivalent to the 2 category of local systems of categories on C star. So in other words, what is a local system of categories on C star? Well, it's a category together with a monitor, right? Because a local system on C star, local system of anything on C star is whatever it is. So this is, in other words, the 2 categories. These objects are a category equipped with an automorphism T. So now we can prove 3D mirror symmetry. maybe I will do on this board here. Maybe I'll do it over here. I know I can. Let me do it down here. Sorry, I'm gonna erase this. So this is going to be the basic proof of 3D mirror symmetry. So I should say I learned this from Konstantin Talman's 2014 ICM address. Although then I talked to a physicist who told me this is just known to physicists of particle vortex duality. For a long time, you exchange this winding modes along C star with a gauge particle on a mirror, which I'll say in a moment. So what's the situation here? Just so that I can keep my C star clear from its dual C star, let me let T be C star. That way I can tell the difference between T and T check. So what am I saying here? We've said that this Coder 2 category is equivalent to the category of local systems of categories, which I'm calling 2 load, on the base of my cotangent bundle, which is this torus T equals C star. That we've explained is just module categories over a linearization of this monoidal category here, which this D here is, of course, the category of base is the sort of discrete category of base loops of C star. This is base loops on T, module categories. So I'm thinking of this base loops on T, linearization of base loops on T as a monoidal category. I can take its 2 category of module categories for that monoidal category. Of course, this thing is, of course, just the category of representations of the dual torus. Rep T check with its monoidal structure of tensor products, module categories. Of course, representations of the dual torus is equivalent to quasi-coherent sheaves on B of the dual torus, on the classifying stack of the dual torus. So in other words, this 2 category here, which I've sketched, is equivalent to a 2 category with one object, such that the endomorphisms of that object are quasi-coherent sheaves on this stack. And that matches up exactly with what I said before, is the KRS2 category of the pair of cotangent bundle of the stack BT check with its sort of Lagrangian given by the 0 section. L equals BT check. Great, because what did this mean? This meant that I'm supposed to consider the KRS2 category of this cotangent bundle, but I'm just considering the single object, which is the 0 section, and the endomorphisms of that object are coherent sheaves on it. So they have the size issues, whatever, are coherent sheaves on it. Therefore, this 2 category is equivalent to the 2 category of module categories for the endomorphism category of that object, which is this. Well, so I said the group G was just sort of to say that you can allow yourself to be a stack. And so in this case, the group G here was with T check. So this is, I'm taking the cotangent bundle of a stack. So the point was, if instead I took cotangent bundle to a stack, you can imagine I take cotangent bundle to a point, which has a Hamiltonian the trivial action, and then I take the cotangent. This is just to say that the mirror of this cotangent bundle of C star ended up being the cotangent bundle of the classifying stack of the dual C. So sorry, I know this was a lot of very fast categorical manipulations. There are some relations. So the question is about the relations of any geometric Langlands program. There are some relations, but that's an equivalence of, I mean, you might say 4-dimensional field theories, TFTs, and this is the equivalence of 3-dimensional TFTs. So there are some cases when you can reduce that 4D TFT on a circle, and you can you can get yourself in a situation related to this. Or you can also, I see, maybe what you're asking is, can I think of these things as boundary conditions for the 4-dimensional geometric Langlands? And then the answer is absolutely. That if I have a 2 category with a G action, That's the same thing as promoting my two category to an object of a three category of two categories of G action, which is part of the Betty geometric Langlands picture. For G of torus, this sort of Betty geometric Langlands duality, sort of we wrote something about it in our paper with Justin and Aaron. Okay, so that may or may not have been helpful. Let me just sort of formalize what I've just said here in a conjecture about this Futter two category. So if you sort of tuned out for a while, you can tune back in, because now I'm telling you what I think this Futter two category is in a cotangent bundle. So the conjecture is first, if I take the Futter two category of T star M, where I take my sort of skeleton to be M itself, the zero section of this cotangent bundle, then I believe that this should be the two category of local systems of categories on M. I should say that in addition to sort of our work with Justin and Aaron, this conjecture also came out of some discussions with Simon Resnick. So this should maybe I should say that this relation categorifying the sort of maybe more familiar relation that the Fukaya category of the cotangent bundle is equivalent to the category of local systems on the base of the cotangent bundle, where the only difference now is that this is a Futter two category and this is a holomorphic variety instead of a Fukaya category and cotangent bundle of a real manifold. So that's the first kind of conjecture. And already, as you can see, you can do a lot with this conjecture. If you believe it, then you can prove this 3D symplectic correspondence here for the cotangent bundle of C star. But of course, the more interesting thing is where you allow your Lagrangian skeleton to be not a smooth thing, not just the base of the cotangent bundle. So the second conjecture, which I'll put down here, is that the Fukaya category of T star M with a general conic Lagrangian L as its skeleton should be equivalent to something I will call 2-perv ML, where by definition, what I mean by this is this 2-perv is the two category of perverse Hilburns, two category of perverse Hilburns. This notion is due to Kapranov-Shefman. On M with singular support in M. So unfortunately, this two category is not very well defined in most cases. We only know the definition in a few cases. There's a sort of several groups sort of working to understand this perverse Hilburns better. I should say a lot of the progress seems to come from the sort of Tigerhoff school, but in addition, there's several other papers, Kapranov, Shefman, Soyman, Sukhanov, lots of people are investigating this. It's very exciting. I'm going to study the cases where we know what this is. And let me say that in the cases where we know what this two category of perverse Hilburns is, what it's meant to do is it's meant to categorify perverse sheaves. So this sort of equivalence here, this conjectural equivalence is meant to categorifying the sort of, again, by now, hopefully somewhat familiar relation that Fukaya category of T star M with a stop given by the sort of non-compact skeleton L is equivalent by the sort of Binatra, Pardon, Shenda, and earlier Natter-Zaslow type theorems to a category of sheaves on M with singular support in M. So the sort of, if there's one moral you take away from this talk, it's that if you're studying a pair of cotangent bundles of holomorphic varieties, then you can try and study, instead of studying this Futter two category, which we only barely know what it is, you can try and study this two category of perverse Hilburns instead. And you can see if that category has some spectral decomposition as it did in this case. And sometimes it would. So maybe the moral is kind of just, if you think of Fukaya categories as having to do with some sort of, Fukaya categories are about homological algebra, then this Futter two categories are about categorifying homological. which seems to be the motto of the Decomposition school. Okay, so now maybe I better actually say what we can do with this perverse Schober's stuff. So I'm going to give essentially one example, and then variations on that example. But it's going to be quite a powerful example. And it doesn't talk. Okay. So what's the example that I want to consider now? And I want to consider variations of this example for the rest of the talk. It's the example where X is the cotangent bundle to C, and my Lagrangian L is the union of the zero section together with the cotangent fiber to. So here's a picture of my Lagrangian L inside of T star C. So I'm no longer dealing with just the zero section. And so luckily for us, well, luckily for us, we know what the two-category perverse Schober's is in this situation. Perverse Schober's on C, whose singular support lies on the conormal to a single point in C. Perverse Schober's, in this case, CL, is equal to the two-category of spherical adjunctions. I'm about to explain what these are. Adjunctions. So I should say this notion of a spherical adjunction came from Rina Ono first, and then some work with Ono, Blankeneko, building on some earlier work in the Kaya category on twists around spherical objects. I guess by Seidel, probably Seidel on Seidel, sure. Some of that happened later too. Okay, so what are these spherical adjunctions? I should say that, yeah, so again, I've been having some talks with Simon Rezchikov. I think it should actually be doable in this very simple setting to like write down the Twitter 2 category and prove that you do in fact get this. It helps to know what the answer is ahead, basically. So what is this 2 category? So it's what is a spherical adjunction? I should say that these are more commonly referred to as spherical functors, but I think it's better to call them spherical adjunctions because it's a more symmetrical way to consider the whole adjunction once and not just one functor or the other. So a spherical adjunction is, well, first of all, it's an adjunction. So it's a pair of categories, C and D, with a functor F between them, and its right adjunct functor FR. So of course I've already broken symmetry by declaring this is F and this is FR, and so maybe this is F and this is FR. So from this adjunction, I can form 2 endofunctors of these categories here. Namely, I have the unit map from the identity of C to the to FR, and I have the map from FR to the identity of D, and I can take the cone on each of these natural transformations, right? This is a natural transformation of functors, so I can take the cone or shifted cone, I'll say fiber or co-fiber of these things, right? You should imagine I'm taking the sort of this, the fiber fits into an exact sequence on the left of this map, the co-fiber fits into an exact sequence on the right of this map, and I'm going to give those things names. I'll call this one TC and this one TD. So I've just defined 2 endomorphisms here, 2 endofunctors here. TC is an endofunctor of C, and TD is an endofunctor of D. And by definition, the 2 categories of spherical adjunctions consists of those adjunctions such that these endofunctors are inverted. Okay. So for those of you who are familiar with the standard definition of perverse sheaves on C with a singularity of 0 in terms of nearby and vanishing cycles, this should look very familiar, right? In that setting, you also have a pair of vector spaces, that sort of nearby cycles, vanishing cycles spaces. You have a pair of maps between them, and you have the rule that's sort of the difference between the composition and the identity, that is like 1 minus xy. That has to be invertible, an invertible operator on both sides. So this spherical functors or reverse Hilburns are sort of hooked up to exactly categorifying evaluation. And so it turns out that that was not just a pleasant guess, but it actually is something that I think pops right out of the sort of Hooter analysis of this holomorphic symplectic map, which is a sort of basic building block in a lot of the holomorphic symplectic manifolds that people have. And maybe I can remark that if I just forget about these, functors here, and just think about this C and D with their auto pointers here. Okay, so these things are invertible. If I just remember this C with its auto equivalence TC and D with its auto equivalence TD, I remember from the thing I just erased that a category with an auto equivalence is the same thing as a local system of categories on C star. So sort of these things here are local systems of categories on the smooth part of F. Right, my Lagrangian L has a singular. Its smooth part is just two copies of C. And so this is saying that just within the theory of sort of perverse sheaves, I can restrict my perverse sheaf to this open subset, or I can do a Fourier transform to restrict, or equivalently do a sort of micro localization to this open subset here. Likewise, my sort of perverse chamber restricts to a local system of categories on this open subset here, or micro localizes to a local system of categories on this open subset. So that's very pleasant. And somehow this is what this is saying is that the additional sort of glue of these functors is sort of really what's happening at this point. Let me, before I state our theorem, give some examples here. So again, the notion of spherical functor is kind of ubiquitous in algebraic geometry for the reason that if I have D is a smooth hypersurface inside of a smooth algebraic variety X, D smooth hypersurface, I didn't spell that right, whatever. Then if I have coherent sheaves on X, and I have the pullback to coherent sheaves on D, which is left adjoint to the push forward, this thing is a spherical adjunction. So basically, anytime you're pushing forward from a divisor, that's a spherical adjunction. The second example, which I'd like to give of spherical adjunctions, is, well, let me state it this way first. There's an adjunction between filtered vector spaces and graded vector spaces, where on the one hand, I take the associated graded of my filtration, and that gives me a graded vector space. On the other hand, I put my graded vector space with the trivial filtration. And this is a spherical functor. And in fact, this is exactly something of the previous situation, where now my variety X is not a variety, but a stack. So if I take coherent sheaves on C mod C star, the Reese construction tells me that coherent sheaves on C mod C star are the same thing as filtered vector spaces. Graded vector spaces are the same thing as coherent sheaves on 0 mod C star. And of course, 0 mod C star is a divisor inside of C mod C star. I once again have this pair of adjoint functors given by pullback and push. The reason why I've given you this example after this one, this example might seem nice and simple. Oh yes, this occurs all the time in algebraic geometry. You might ask, where did this example come from, or equivalently this example? And where it came from is that this is the universal case. This is the universal inclusion of a divisor, I'll say, in the sense that if I think about what a divisor is, right, it's it's cut out by a section of a line bundle. And if I think of line bundles with section, so if I have a line bundle L on X and it has a section S, a line bundle on X together with a section is the same thing as the data of a map from X to C mod C star. So somehow, like this situation here, that's the sense in which this situation is really kind of universal. And now I'm going to give you another sense in which that situation is universal. And you can take that little bit here though as motivation for the theorem I'm about to tell you. So theorem, this is my paper with Aaron and Justin. So maybe the first statement of the theorem is just in the two categories of spherical functors. So I said that our goal is to understand this two categories of spherical functors, to find some spectral description, find some description of it in terms of coherent sheaves on plots. And it turns out that this thing here, filtered degraded vector spaces, which is this spherical functor, is very important. Namely, if I take Hom inside the two category of spherical functors, or spherical adjunctions, whatever, between this spherical adjunction, this spherical adjunction, effect, figure effect. If I take Hom in the two category of spherical functors between this and any other spherical adjunction, C to D, then its Hom category, this is a two category, so Hom between these will be a category. Its Hom category will be the category C itself. So in other words, this spherical adjunction co-represents the functor of take the nearby cycles category of your spherical adjunction. Take the nearby cycles of your reverse show. And similarly, if I sort of did this adjunction the opposite way, I would have a functor co-representing take the vanishing cycles category, which let's say nearby. Well, one of them is nearby, one of them is vanishing. Take the other category of your reverse show. So you can imagine that this. Yeah, so I didn't say this, but we write if this is why I call them spherical adjunctions instead of spherical functors, that the right adjoint to the spherical functor is also a spherical functor. So I can replace this adjunction FR with FR. And that gives me a spherical adjunction where the role of the categories is constrained, which you can think of as a Fourier transform, right? Turn my head sideways and I think that this is the base of my reverse Hilburn is rather than. So there's all these remarkable symmetries of spherical adjunctions, which I don't have time to get into, but they allow me to perform this trick, which ends up giving me this theorem, which is a corollary, which is that, so I've seen now that, well, I'll just state the corollary this way first, and then we can discuss it. So the corollary is that the two category of spherical functors is equal to the category of coherent sheaves, equal to the two category of module categories. Which, okay, let me write this down and then I'll say what it is. So this is C mod C star disjoint union 0 mod C star, fiber product over C mod C star with C mod C star disjoint union 0 mod C star module. Okay, so C mod C star disjoint union 0 mod C star. This might look like it came out of nowhere. This thing maps to C mod C star. I can take the self fiber product of it over C mod C star, and that gives me and then take coherent sheaves on that whole thing. That gives me a monoidal category, and I can take the two category of modular categories for that monoidal category. So what the heck is this? So I claim, first of all, that this category down here on the right-hand side is my KRS2 category of T star C mod C star with the same Lagrangian F, where F is the union of the zero section and the quotient pi equals to 0. So I should explain why this is. So let me work out all these fiber products here. So this is coherent sheaves, this is modules over coherent sheaves. Module categories over some matrix of coherent sheaves, right? I'm going to have like 4 different components here. I'm going to have fiber product of C mod C star with itself over C mod C star. That's coherent sheaves on C mod C star. I'm going to have fiber product of C mod C star over C mod C star with 0 mod C star. That's 0 mod C star. We get another 0 mod C star. And then finally over here, I'm going to get 0 mod C star fiber product with itself over C mod C star. Okay, so these are the 4 components in this fiber product. So this you can take as a sort of authentic, complete definition of the KRS2 category in this case. which has to do with the fact that, well, so I told you before, if we have smooth Lagrangians meeting cleanly in smooth intersections, then the endomorphisms of any one of those Lagrangians should just be coherent sheaves on itself, and the column from one Lagrangian to another should be coherent sheaves on the intersection. And there's going to be some twist involved, possibly, in some of those computations, which is going to have to do with this bottom right component here, which you might say looks out of place because I wanted that bottom right component to be endomorphisms of this vertical Lagrangian. Like this KRS2 category here is supposed to be generated by the two components of this thing. And the bottom, the top left corner is endomorphisms of this, the bottom right would be endomorphisms of this. And of course, I'm using the fact here, that coherent sheaves on the fiber product of 0 with itself over C is equal to modules, perfect modules, over a ring in one variable, in one degree 2 variable. Maybe I should call my field C, degree 2, which I should think of as a sort of functions on, I should think of this as some two shifted version of coherent sheaves on this thing. In general, the KRS2 category is only defined as a sort of, the Hom spaces are two periodic categories rather than DG categories. So, okay, that may or may not have been very helpful to people. I have 2 minutes left to state sort of further application. But this is supposed to be, I don't know, this is supposed to be the prototype for how these equivalences go, is that someone tells you, I have some holomorphic symplectic manifold, and you study its Futter-2 category, or maybe you study some other sheaf theoretic incarnation of its Futter-2 category, which is going to, have some, possibly quite, involved amounts of morphisms, two morphisms, things like that. And somehow you present this as some sort of category that's defined purely in terms of algebraic geometry. And now I can compute all of the Homs among these categories, very easily and straightforward in a straightforward way by studying coherent sheaves on C mod C star, 0 mod C star, etc. Okay, I have 2 minutes left. I can give a very quick application, very quick pointing at least towards sort of where you want to go with this. So 3D mirror pairs, I'll end my talk with this. So we've already discussed how if I take X is equal to the cotangent bundle to a torus T, then X check is equal to the cotangent bundle of the classifying stack of the dual torus T check. Maybe a more general, well, let me just give 2 more examples, which one of them is that if X is C2 mod C mod n plus 1, if X is the resolution of that symplectic singularity, then X check is going to be the cotangent bundle of e to the n. And finally, let me say that if X is just in general the cotangent bundle of V mod G, where V is a vector space and G is a representation. Maybe I should say if G is a symplectic resolution by singularity, I'll do it this way. Then its dual space X check will be this BFN Coulomb range, which seems quite complicated. And so your goal is going to be ultimately to investigate 3D mirror symmetry in this setting. The point I would like to make in the final minute of my talk is that this second line here, both of these fit into this setting in a simpler case where G is a torus, right? This one is the cotangent bundle of C to the n, C to the n plus 1 mod C star to the n. And this one is the cotangent bundle of C to the n plus 1 mod C star. And both of these embed inside of this line here. These are these toric hypertalar manifolds or hypertoric varieties, originally defined by Gotha, then studied by Bielowski Dancer, and these all embed into the cotangent bundle of C to the n modulo a torus as the stable locus inside of this stack. So you can study these by studying the cotangent bundle of C to the n modulo torus, and we've just told ourselves how to understand the two categories associated to the cotangent bundle of C to the n. And in this paper, we also explain how to do it for C to the n modulo torus. And so therefore, in sort of forthcoming work with Justin Hilburn, we're going to prove the symmetry equivalence that's going to relate these general hypertoric varieties to each other. And then ultimately in the future, we hope to extend that to these BFN and Coulomb branch settings. So I'll end here. Thanks.
Thank you.